Great. So, hi, welcome to this week's NPL seminar. I'm Panda, and it's my great pleasure to introduce Fabian Ruffy Varga. So Fabian is currently a second-year grad student at NYU, though currently he's coming at us from Germany, where he is enjoying the better beer or something.
Yes.
So Fabian's going to be talking about Gauntlet, which is some work that he and his collaborators, Tao, and his advisor, Anirudh, have been doing, where they're looking to verify the transformations that the P4 compiler is doing. So they're trying to do translation validation as a part of making sure that the compiler is actually optimizing code correctly. And this is work that's going to appear at OSDI later this year. Fabian.
Thank you. Thank you, Panda, for the introduction. Good afternoon, everyone. I'm a grad student at NYU, and this talk is going to be all about the P4 language. So, in essence, we're going to talk about how we want to find bugs in P4 compilers and why we want to do that. How we actually try to develop a method that combines fuzzing and formal methods to find these bugs. Then the tool we built based on these methods, Gauntlet. And then we briefly talk about our results in the future work and future ideas we have. Cool stuff to do with P4 compilers. So I think everyone here is probably broadly familiar with the P4 language. It is an instruction language for network devices or network targets, which allows you to basically specify how you want to process or forward a packet. And in essence, the language specifies a packet processing pipeline. The nice part about it is it has a compiler, and you can use this compiler to load your binaries, so it's very flexible, and it's completely open source and standardized. And this language has been around for a while now, since 2014, so it's almost 6 years. And since it's already been 6 years, the language has matured a lot. At least in my opinion, it has reached a stable state with the P4 16 specification. And it is also being increasingly and slowly adapted and adopted by commercial enterprises. So, for example, Barefoot has been a company that has been founded based on the P4 language. There's now Cisco, which is coming forward with the Silicon One chips. There's Xilinx, which is developing FPGAs. And there's also a broad range of users who are interested in using this language for all kinds of purposes. Google for specifications. Broadcom also is part of the Stratum project. There's Nokia with 5G efforts. And even Princeton, I heard, that uses it in its campus networks. So this language, P4 16, it has a reference compiler called P4C. And its status is somewhat similar to GCC or LLVM, where it is supposed to be the reference compiler for the language itself. So it represents the language specification. So when a user wants to use P4, they use this compiler and they generate an intermediate representation, which they then can convert to target-specific instructions for their network device or whatever they want to use P4 for. P4's job is broadly what a general purpose compiler front-end does. It transforms the input and it provides a general library of passes that streamlines the code and makes sure the code is of a certain quality. So it's desugars and everything. The way this looks like is also pretty standard. The compiler takes a P4 program, it feeds it into the parser, and the parser generates an intermediate representation. And this intermediate representation is fed through the front end, in the mid end, and in the back end. And this always stays the same. So you want to make sure that well, the compiler keeps a consistent IR. And in the front end, in the mid end, you will have several target-specific nano passes or transformation passes that somehow transform the program in a more standardized form. And in the back end or mid end, usually the user can customize what they want to do. and use a different kind of pass. Well, the issue is this is a lot of code, and there's a lot of transformations going on in this compiler, obviously. And you cannot be sure that this doesn't have bugs. So there can be bugs anywhere, in the parser, in the front end, in the mid end, in the back end. And we don't really know if you foresee the compiler itself compiles correctly. But if you think about it, this code will run on mission critical equipment, on data center switches, on network devices. It might be used for specifications. So we really want to make sure that whatever P4C compiles stays correct. And it's really hard to debug network equipment. So if you have a faulty packet processing engine or anything like this, it might be pretty difficult to detect this bug. Obviously, prior research and compiler bug research has shown that even very mature compilers, such as GCC or LLVM, have hundreds or even thousands of bugs that cause miscompilations or invalid transformation. And so we believe P4C is certainly no exception. And what this means for us, we want to make sure that, well, P4C is correct. But how can we ensure that? And this is the premise we set out. And we asked ourselves, how do we actually test a compiler? In that context, we were looking at Nick Kiemann's work and his differential testing work. And he proposed 7 stages of how you could test a compiler. So you first start really simple. You have level 1, which is just a random bit stream, and you see if your compiler actually crashes with this. This could be very easy. Then after that, you start with actual words, and you test if your compiler can transpose these words or process them correctly. In the next step, you start with a syntax. And then you should have a parser that enforces the syntax. Level 4 is getting more interesting. If you want to have types in your compilers, you want to ensure that the types you have are also enforced correctly. So in the context of P4, if you have a header type, you don't want to just add ints to it. This should be an error. Now at level 5, you want to confirm your syntax and your parser. You should confirm to some form of specification or make sense in the code you write. So in P4, this means that in certain contexts, like a function, we shouldn't be able to call as exit statement or similar classes of statements. In level 6, you will get into very sour territory where you want to ensure that the compiler doesn't alter dynamic properties. For example, in P4, headers might be valid or invalid. If you transform this program, you want to make sure that the header stays invalid if it was invalid before, and the compiler doesn't change this property. And level 7, the more subtle level, just implies anything. In the sense of, if you have a P4 program, it corresponds to a specific model, and that model might be a semantic model. And anything that deviates from the semantic model after you compile this program is incorrect. So any input that leads to according to your notion, wrong output. Well, in the P4 ecosystem, we observed there wasn't really that much when we started out. There was a fuzzing tool, but it was fairly basic, and there was general purpose tools like American Fuzzy Rock. And we wanted to go further and cover the last 3 layers where you get into these specific subtleties of how you could test the compiler. And again, based on classical compiler literature, we classified and looked for 2 types of bugs in our work. First, there's the obvious bug, a crash bug. Any program you use that causes your compiler to terminate abnormally, so that means a segmentation fault or some weird error message, we consider a crash bug. Because the compiler should always reject programs that are incorrect. It should never crash. And in our notion, these are all the programs up to level 5 in which the compiler should enforce that the program that is invalid stays invalid and is not causing issues with the compiler itself or confuses the user. The more interesting and more subtle bug is the semantic bug or the miscompilation. Here, the compiler doesn't raise any error. It just compiles a program and produces a binary. And this binary is wrong. So if you feed an input, you get the wrong output, which is basically the last two levels we're dealing with here. And these are very tricky because the user doesn't know that anything is going wrong, and he sees wrong behavior, but blames its own code. But it's a compiler, obviously. So we have these two types of bugs. How do we personally find them? Well, we target level 5, which is statically conforming programs, because we believe that P4C, the compiler itself, has been around for 3 years and has been mature enough. So what that means is we generate programs that are generally considered valid, but might lead to a crash in the compiler itself. And then we want to ensure why, we want to understand why it crashes and how we can prevent this. So anything that causes a non-zero exit code, basically. Maybe an out-of-memory error, a timeout, or anything that also is incorrectly rejected. The nice part is once we have this generator, we can use the programs to generate to also tease out these more subtle bugs at the end. And how do we find these subtle bugs? In essence, there has been a lot of work in general purpose languages for CLang or the GCC compiler, trying to understand how you could find out and make sure that your program generator or your interpreter is correct. And the essence behind this is you are dealing with the oracle problem. You need some kind of oracle telling you that, that for a particular input, this compiler produces a wrong output. And there have been several approaches in the past. And we were looking at 3 of them, which is A, compiler verification. And compiler verification essentially means you write a proof. Ensuring that each pass you apply can never be wrong. And there have been examples like Concert in the past, which uses restricted C, and applies restricted C. Well, the problem with it is it's very nice and very clean, but it's also costly and very inflexible. And at this stage in P4, we were not ready to really write a proof generating compiler or any proof generating tools because the ecosystem is still too young for this. And also you would have to write these proofs for every target architecture and each dialect of the P4 language, which cause many man hours, and we are a small team. So we discarded this possibility. The second option we were looking at was differential testing. And differential testing mostly broadly means that you have many compilers or multiple compilers for the same program, and you observe how they compile a program, whether they reject it or not, and what output binary they produce. And if at any point for the same input, the output of this binary differs for various compilers, you can be sure that one of these compilers in all likelihood has a bug. It is also a very neat technique because you don't have to use an oracle, so you don't really need to know that the compiler is doing something right. You just compare and see. You observe differences. But in P4, again, since we have so many different target backends and so many users using the different applying the backends, we don't really have 2 compilers for the same target. And this is just a practical limitation. And we as a research group were also, we didn't see the use of just producing a compiler just for the sake of differential testing. So we ended up with the third option, that is, as Panda said, translation validation. And in translation validation, you infer a semantic notion of a program, and you compare the input, the semantic notion of this input, with the semantic notion of the output. And you observe and try to understand if there's a difference in these 2 semantics after the compiler has processed your program. In the past, this has been fairly difficult to implement because of, well, equality is an undecidable problem for Turing-complete programs. But in our case, P4 restrictions have given us a great advantage in how we could leverage translation validation. So we use translation validation, and it is traditionally limited, but there are certain properties in P4 that gives us great leverage. First, the language is not Turing complete by design. All the loops are bounded in the parser. Everything is statically allocated, and you cannot execute any arbitrary code loop. There's no pointers. And also, the program has this pipeline structure, which makes a very well-defined state, broadly speaking. At the end of the function, you really know all the essential output you need, which is the packet. So you get an input packet, you produce an output packet, and there's always going to be some form of this. And it's also possible for you to really track what kind of state is modified, because it will be specified at the end of the output. What this means for us, compared to the past, where translation validation had to use a lot of tricks to be effective, we can just compare entire programs. And we just need to get the semantics for one program, compare them to the semantics of another program, and we can check for equality. And we don't have to worry about any of the classical problems of translation validation. And based on this hunch or notion, we have built a Gauntlet framework. Gauntlet is an application of these ideas. It's a toolbox of testing software, and it has a random code generator that produces random programs, then an interpreter that produces semantics for a P4 program, and then C, this translation validation and testing pipeline, in which we check every single compiler pass and observe if there's a difference before and after. So these tools use three techniques, which is the random code generation to find the crashes, translation validations to find miscompilations, and then as a bonus, since we already have semantics, we decided to use symbolic execution or model-based testing to identify bugs in closed source compilers. So if we cannot apply translation validation, sometimes we just have to run a simple test with expected input and output to see if there's a discrepancy we could probably, hopefully identify. So the semantic representation I talked about, what does it actually look like? We really rely a lot on C3, the SMT solver. It's very, very useful for us. And what we do is we present a P4 program as a simple C3 SMT formula, mostly C3 Python. And it's just a single data type function. And what it essentially represents is the input and output of the program, which is the packet or metadata you might have. And at the end of our interpreter, this final expression will just be a data type. And it's a single Z3 data type, which has many if then else branches. And each branch is just a branch in the state of the program. So a table or a conditional that might occur. Ultimately, we've done this for a couple of months, and we implemented large portions of the programs fairly quickly using our semantic representation techniques. Let me show you an example. If you look at this program, a P4 program, it's a fairly simple program that applies a table, and this table has an action, which is called assign. So we have an input header, and this input header is just assigned to value 1. And we may choose this action if the key in this table matches exactly. Otherwise, we don't do anything. There is no action. In our representation, what this looks like is just a simple if then else function where if the symbolic key of this table, so if we have a match, is matched, and the action is 1, so that means the action that is chosen means assign, then we will return a header which value is now 1 in its input field. So header 1, header B means that this header has been assigned the value 1. Otherwise, in all other cases, if we don't match, or if we don't choose action 2, if we don't choose action assign, then there will not be any action being done, and the header will just go through the program as is. So we've written this interpreter, and it's essentially an extension to the before compiler. So it uses a lot of P4C tools, and it's IR. We made sure it's very target independent. So it only needs a P4 program and its model, so just an include file, to produce semantics. And it's also designed to handle really all forms of the P4 language. You don't do anything that does the sugaring, or you don't use any passes to streamline the program beforehand. We really just try to accept whatever the program wants from us. Whatever the program is represented as, and it's valid before. Our interpreter is extensively tested, so we try to pass all the 600, 700 tests of the P4 compiler, and we also use over 100 custom tests, which most of these custom tests come from just our program generation. And there have been programs that have not been covered by the traditional P4 compiler tests. Coming to the techniques. Well, our first tool is called Bludgeon because it's a random program generator, and it's modeled after the Grant C-Smith, which is a random program generator for C. However, as opposed to C-Smith, we really don't avoid undefined behavior at all. We explicitly accommodate it, and we try to handle it as much as possible, which makes our random program generation a lot simpler. Bludgeon is also written as a P4C extension, and it is really just growing the abstract syntax tree of a simple P4 program stochastically. So every iteration, it chooses a random expression to grow until it terminates.
Hey, Fabian,
yeah.
Can I ask you to pause for a second? So Nate has a question, but he might have to leave early, so he wants to
I don't
ask
see that.
now. No, he's just gonna ask you. It's fine. I should MC this anyways. Sorry, Nate. Go on.
Okay. Yeah.
Hey.
Sure.
Can you hear me? Okay. Yeah. This is cool. I was curious if there were. So when you generate this SMT formula, there might be some operators in P4 that are hard to encode in SMT. I think like a hash function might be a typical example. So I'm curious how that's handled.
Okay, so operator hash function. Hash functions have been so far encoded as externs, as far as I know. I've not seen, well, in the IR, I have not seen a hash function operator. And right now for externs, they essentially work in some form as an uninterpreted function. They generate a random value. So a hash function has no meaning for us.
I see. So you over approximate it as it could be any function, and then
yes. And as far as I know, there is no compiler pass that does anything with hash functions so far. So we've been lucky in that sense. But if there would be a compiler pass that has explicit semantics how to process and modify hash functions, we would need to assign explicit semantics to this extension. And we have written an extension model where we can implement specific semantics for these externs, but we have not really used it so far. It's not very mature. Yeah, cool. But essentially that's what we do. So it's like some kind of cop-out, but really we haven't had to deal with it, thankfully. All right. Yes, so this random code generator, we try to guide it according to the P416 specification. So if a program is correctly rejected, this means our random code generator has a bug. And at the same time, we try to limit the size and try to generate small fragments of the language that limit branching so we can avoid a huge state space explosion in our random program generation. Some more design details. Since P4 has a lot of different backends and a lot of high target diversity, we try to make this random code generator also quite flexible. And each backend is a template which defines what declarations we need to produce and what kinds of program types we want to fill with code. We use probabilities to configure our generation of expressions. So if there's some target backend that doesn't support some specific expression, we set the probability of this expression 0 for this backend. Right now, if anyone is familiar with the backends what we support, is the V1 model, Tofino, and the new PSA backend. It's very simple to use. You just call Rajan and you specify output file and a specific architecture you want to use. Coming to technique 2, which is not the random code generation, but our validation pipeline. The way it looks like is you first generate a random program, then we compile it with P4C. If it crashes and you have a non-zero exit code, then it is a crash bug. Otherwise, we emit the immediate representation before and after each compiler pass. And we feed each of these programs into our interpreter. And at the end, this interpreter generates this free representation, and we compare each of these programs against each other. If everything works out and there's no complaint, well, the program has compiled fine. If that is not the case, we need to do a second check because, as I said, we try to accommodate undefined behavior. So it might be the case that there's a difference in undefined behavior, which for most compiler developers doesn't really matter. And we do the second check, and if after this check we know it's caused by undefined behavior, we just mark this as unstable code and say, okay, this is maybe slightly dangerous. We're just gonna put it on the side and maybe notify the developers. Or if we know it's not caused by undefined behavior, this is a real bug, and we should definitely notify the developers. There are some details, of course. We also use P4C facilities again, and we parse everything that is emitted by a P4C tool that is called 2P4. And at any stage in the processing pipeline, you can generate a P4 program of the intermediate representation, which is a really neat thing. And our semantics are essentially a normalized representation of a P4 program. And this representation at the end is tainted by undefined behavior, but it's still going to be a representation of the program itself. Again, fairly simple. You just have an input file, and this entire script will handle the validation for you. Lastly, our last technique is the model-based testing, which is our technique we use to find a bug in in closed source compilers. For example, the Tofino backend, we don't have access to the AR, so we don't know what's going on there, so we cannot dump any pass. We cannot use translation validation at all. And so we use our semantics we have to also do semantics checks. And essentially what we do is we do the same thing, we generate a program, we compile, we check for a crash bug, but compared to what we do in translation validation, we actually load this program into the target device. And we use our interpreter to generate Z3 and then generate test files. And these test files have an expected output. We feed these packets in, we record the output with Wireshark or any network tool. And then we can see and try to identify if what we recorded matches with what we expected. If that is not the case, we know there must be something off. This could be a very high likelihood of validation bug. Otherwise, this is a programmer has run fine. To handle undefined behavior, we mostly use I don't care arguments in our tests because undefined behavior and real hardware is kind of weird. So you essentially have to ignore everything. You cannot really have any expectation of the output. This is also a great weakness of model-based testing. Essentially, what you really require is a test framework, and you compare input and outputs based on different branch conditions in your program. And what we produce in the context of P4 is called STF files or PTF files for the Tofino or Barefoot backends. And what we cannot really do is support table entries right now. We just haven't implemented it. So we try to avoid generating tables for model-based testing because we cannot configure the table entries from the control plane. Again, the usage is very simple, just input output. Lastly, just a quick example of how these bugs look like in P4. You have this program, which is a simple control pipeline which assigns a value to the iter type of your header. And if your type is 0, it assigns IPv6. If the type is not 0, it will just assign IPv4 as a type. But after the def use analysis, what happened was that for some reason, there was a bug in which def use removed the assignment because it thought that this assignment would be overwritten by the later assignment from IPv4. And if you're a programmer, this can be a really frustrating bug because you don't understand and you don't get to see, don't see that an IPv6 assignment in the code at all. Our tool caught this and we filed this bug. And this is broadly the nature of bugs you can find in the code. Oh, there's shit. Yes, caused by undefined behavior. Yeah, there's, thank you for this question. This is a very good question. We explicitly model undefined behavior in our interpreter according to what the spec calls undefined behavior. So uninitialized variables are broadly the most common case. And they happen if you have parameter modes in your functions or in your actions, which they're called in, out, or in. If you have this parameter mode called out, the input is in some sense reset and it becomes deinitialized. And if you don't deinitialize this assignment, then this value is undefined. And it can be anything. And this permeates throughout the entire program. There are other cases where you can have undefined behavior. For example, if you set a header invalid and set it valid again, then the values of the header are undefined too. Does this answer your question? Okay.
Yeah. I assume that we're largely waiting till the end for questions. I mostly broke protocol before because of timing constraints. So if you need to ask an immediate question, if you just mark it, I can interrupt Fabian rather than having him trying to look over the chat.
All right, thank you. We are almost done. So we have all this work, and we also track these results, obviously, because we like to quantify data. We, in a total of 8 months now, so September, we started in January, we found 96 compiler bugs. The majority, obviously, crash bugs, but we also found around 34 semantic bugs. And what is interesting, we found a lot of crash bugs in a real hardware target, which is the Tofino compiler. And we also find several semantic bugs in the backends. And this is a lot of bugs for production tools, which is understandable because it's very complicated code. But this also means there's a real danger of having undefined miscompilations in your production system. Also, our bug submissions resulted in 6 specifications changes. So we raised edge cases that needed some reconsideration. And the thing I like the most personally is that after we wreaked havoc in some sense, Gauntlet, our tool, is now part of the continuous integration pipeline, at least the translation validation tool. So every time you do a commit in the P4 compiler, our tool runs on all the tests and new tests that you supply, which is really cool. At least I think it's cool. This is the first time translation validation has really been used in this scale, I think, which is neat. Some details on bug locations in the front end. Most of the issues we were finding were related to type checking, because the front end is responsible for type checking, and a lot of time you just had a crash there. The mid end applies more dangerous and more involved transformation to your code. So this is where we saw a lot of the semantic problems. In the backend, ultimately, because we largely tested the Tofino backend, we found the majority of backend issues in the Tofino backend. But you always have to keep in mind that the front and mid-end bugs also may apply to this backend compiler. And this also applies to the simple switch mid backend or whatever backend you use. There's obviously a lot of limitations. And a primary limitation is that our bug finding techniques, the ones we use, they require semantics. If there's a bug in our semantics, or if they're over approximate, as Nate said, if they're not precise enough, you might have a false positive or a false negative. We also don't really have a notion of what is in between the programmable blocks of the P4 pipeline. So if you go from your parser to your ingress to your egress, what's happening in between, we don't really have a model of this. So we cannot know if there's some problem occurring. This fundamentally limits the model-based testing we use, but thankfully the translation validation is not affected by this. Well, our parser semantics are a little bit immature still, and it's fairly slow to validate large programs such as switch.p4. It's also not very well tested, so we have to be putting some work. And our semantics are specifically tailored for equality checks. So it is unclear to me if they can be used for more yet, because we really honed in on the translation validation, try to make it really precise for this particular purpose. Lastly, we've done all this work, so we obviously have some future work we want to do. And one of them is we really want to push translation validation, because it has been so effective, into compiler backends, which are closed source and inaccessible to us, or which might use a different IR at all. And we want to guarantee the correctness of the entire compilation process, which means we have to find a way to make this these semantics even more general than they are, and understand how we need to model this. We also want to facilitate much more aggressive optimizations in P4C, and we use an idea lifted from Credible Compilation by Martin Linnert, where we may want to skip compiler optimizations if they produce incorrect code. But what this allows us is a compiler developer who wants to experiment a little bit can implement this pass, and if the code is incorrect according to our tool, this pass can be skipped, but it can provide great benefit in the default case. Lastly, we also want to extend the types of work we want to find, because P4 programs work on resource-restricted hardware. And oftentimes, P4 programs are rejected because they're too large, or there's something that quite, the resource usage doesn't quite fit. And this might also be a compiler bug. We don't know. This could be because the compiler incorrectly transforms expressions, and we want to point this out and tell the compiler developers. We also want to see if there is an optimization we might have missed, because if there should have been an optimization, what we observed is a lot of the crashes in the Tofino backend were because people see the front end didn't apply an optimization. So this can be an issue and an annoyance for backend developers. In summary, I'm essentially done. Our toolbox we presented has a random problem generator that embraces undefined behavior. We also developed a target independent symbolic before interpreter, which gives you the normalized representation of a before program. We developed this framework that finds miscompilations in before programming for every step during the compilation pipeline, except the backend. And also tries to find miscompilations on end-to-end and cross-source before compilers, such as the Tofino compiler. With this toolbox, we identified more than 90 bugs, and we were really trying to work with the open source community. And we reported everything, and we tried to get, and a lot of this was considered significant and fixed. And with that, I conclude. Thank you.
Okay, so there's a question from Danny Chin on the channel,
Okay.
Which is, what is the coverage on platform-specific externs like hash functions and registers? As a developer, we experience a lot of bugs when using registers.
Oh, that's interesting. We're just getting started with the coverage for externs. So we have started with the core.p4 file, and essentially it's implementation work. Our coverage is very small, and I think the bugs, they might be, so the front end doesn't do much with registers and hash functions as far as I know. This work is mostly done in the backend of the Tofino compiler, which we don't have access to anyway right now. But we are working on this. So this is part of the future work we're looking into right now. Then there's a second follow-up question I see right now. I can answer that right away.
Yeah, I mean, I wonder, it might help to read it out because I think like the recording for the video won't capture the question itself. So Danny, do you just want to unmute yourself and ask the question, or?
Sure. So I wonder if the packet test cases in your model-based checking are all single packet with single expected output. Because in our case, we found a recent interesting bug where it's kind of stateful. So program was stateless, but we send packet A, B, A. The second packet A will have a different output than the first packet A. So they have different processing.
Okay. Oh, this is an interesting problem. So I think, so we don't really do these kinds of bugs. So these are more, these might be P4 program bugs, but it's unclear to know if that's a bug in the P4 program or the P4 compiler. Yeah, we don't do anything with state. What we do is we just look at the compiler to try to understand how anything the compiler produces is just different from what you have as input. And stateful bugs don't really fit into this domain because the compiler doesn't really modify stateful expressions, as far as I know.
Yeah, I guess.
Although if you have this case, I'm very interested to know about it because.
Yeah, in our particular case, it was undefined behavior by reading reading the header field without checking whether it's valid. I mean, it is valid, but without a if it's valid check, the behavior become wild. But I mean, more particularly, we care more about like, sometimes the entire system should behave in a stateless way, but somehow it's not consistent. So the second time it's the same packet, the model behave differently. So that's why we.
Okay. I see. Yeah, there are other tools actually. P4V, or I think the process group is working a lot on these types of issues, where you look into bugs on which might be called these stateful bugs in P4 programs. For me, out of the description, I don't exactly know if this could be caused by the compiler because the compiler typically doesn't touch this kind of work. If it's undefined behavior, it is usually what happens is that it is optimized away. And it's hard to know if this was a compiler bug or just a program bug. But it could happen. Yeah, there's another question in chat.
Inan, do you just want to unmute yourself and ask?
Okay, sure, yeah. Very interesting work. My key question is what is the key technical challenges this work really address? I mean, in system testing, software testing community, we have seen a lot of existing work, targeting different compilers testing thing. But I mean, P4 compiler I think is one of the most representative compilers. But what's the key difference from this work, between this work and existing compiler testing in general? Because I just want to know what's this specific difference between the state of the art and this work. Thanks.
Yes. Yeah, no, this is a very good question. It's also the hardest question for us because essentially you're right. If you look at it like this, compared to what the general purpose languages do, this is not hard for them. But they have to deal with much harder problems. And we're also just broadly lifting ideas and techniques from these communities. Our main proposal, main approach was to just say, hey, there's this technique called translation validation, which was largely not considered practical or viable in this context anymore. And we wanted to really look into this and see and try to understand if we can repurpose it and make it very effective. And what is different for us, we really have semantics for the entire program, which we can do because P4 is restricted. And what happens if you have this, you can use translation validation in a very effective equality comparison way. And you don't have to use all these domain-specific techniques, which you have in other general purpose compilers, like a live, for example, or what is traditional CREVM and spoof generation. And that's what. But in essence, this is the weakness we have. We don't really have anything crazy new. We just have a very effective tool for this particular domain, which is P4. Does this satisfy you?
Yeah, thank you very much. Yeah, I think, I will absolutely read through the entire paper on archive. Yeah, and yeah, this answered my question. Thank you very much.
All right.
Okay, so Menchi Lu, do you just want to again unmute and just ask a question?
Yeah, sure. So
thanks.
I'm just wondering, so how do you handle the case when a header structure is dynamic and it might require recursive transitions in the parser of a P4 program?
So I see the recursive transition. So recursive transitions, you have loops, but these loops are normally bounded. So essentially, you will just execute the interpreter until the maximum possible amount of loops you can have. And if you make the assumptions that your loop has to move a header, so you can only have a loop really in the parser if you have a header stack, and you have to advance the header stack every time, every loop. And you advance one header stack every time. This is essentially a bound. And if you have an infinite loop in your parser, it cannot exceed the bound, which is the amount of the deepest chain of header stacks you can have in your program. And with that notion, you can, well, bound your loops. The thing is, in translational validation, you actually don't really need these at all. Mostly what you can do is just execute your loop 3 times, and it will also give you an approximation of compiler errors that might happen because of loop unrolling. But what we try to handle the entire loop with this technique. And the second, variable length headers. This is one thing we haven't really implemented, but in P4 compiler, the P4 compiler itself, it has very limited operations on variable variable length headers. So there's not much happening with those. But this is actually an interesting point. We don't really have any implementation for this right now. And this is part of the limitations I have.
Okay, so ultimately, if there's a bound, it has to come from the header structure, right?
Yes, it always comes from the header flags. You can have an infinite loop in the parser, but that is essentially a bug in the program. It should be rejected.
Yeah, I see. I have another question related to the your semantic modeling of a P4 program. So
yes,
we have seen other work on verifying P4 programs, such as P4V. They also use they also translate the P4 program into GCL and then SMT encodings. So how do you compare your encoding with theirs?
So the unfortunate problem is we can't. We haven't had access to P4V.
Okay.
So we tried, and we looked into P4V, and it's just in essence we believed our encoding was more effective for a quality comparison, and they were looking into, well, they were trying to find bugs in P4 programs that are developer rights, and they were looking also into control plane operations and what control plane headers you might insert, which weren't really relevant for our purposes. So broadly speaking, this is the difference. They serve a different purpose, and we don't really know how they look in practice, their semantics. So we couldn't really implement them and try to compare against.
Okay, thank you.
All right.
There are more questions. I don't see any on the chat right
now. I cannot hear you, Panda.
Oh, if there are more questions, I can't see anything on the chat anymore.
Okay. All right. Thank you.
If not, I think, yeah, we can call it. Thanks for the talk, Fabian. I can applaud for everyone else. Cool. Thank you.
All right.